Alright, so in case you don't know who I am, I'm Mr. Caleb Ho. Right, some of my students, some of the students who don't really know me said, "Oh, Mr. Ho, it's rumored that you went to Cambridge." Not true. That's the other Mr. Ho. That's the other Mr. Ho from math. Alright. So work energy power. I was thinking about work energy power and thinking what sports can represent it, because thank you very much. Physics is related in a lot of sporting events, right? When you kick a ball, you need dynamics. When you throw a basketball, you need to go in the hoop, you need kinematics. Alright, so I'm thinking what energy power, what sports best represent it. And just nice, I'm the track and field teacher. Okay? So I'm going to share this with you. I'm going to share my excitement when I see people run. Do you hear anything? Suddenly the sound decides to work. Okay, so this part is not work energy power anymore. I still remember the Olympics, right? When I was watching this one, when this guy runs, it makes me want to run, and right, so amazing. But the question is this, right? As a physics student, he runs very fast. Is there any way to quantify what exactly makes him run fast? Can we make our students run as fast? Hopefully one day. Okay. So the question is this: do we have a lot of? Is it because he's done a lot of work? Is it because he has a lot of energy, or is it because he has a lot of power? Right. And hopefully after these two lectures, you will get some sense. You will get some sense of what it is. So Yoda may say that, hey, the force is strong in this one. Really? Is it force? Well, we don't know, right? But at the end of this lecture, we should be able to tell what is it exactly that causes Usain Bolt to run so fast. And as usual, I'm given a topic with very many objectives, A to K, and let me help you organize this. Right? So once again, A to B will be on work. Right? So please write this down on the front page. A to B is work. C to I will be on energy, and J to K is actually on power. And in case most of you still don't know, right? In the first page, there's actually there's a column on the left, right? Empty column on the left. What's that for? Oh, sorry, on the right side. Empty column on the right side. That one is for you to tick, right? Every time you read the lecture notes, you tick it once. Right? You read that part of that learning outcomes, and you realize you understand it, you put a tick. So by the end, before your A-levels, you should have around 3 to 4 ticks, which should make you quite confident of your understanding. Alright, so overview. I heard a very interesting lecture taught you about forces. Alright, so he applied, so if you apply a force over a certain distance, right, you're actually doing work. Okay, doing work. And the unit of work, can I point out to you, is actually joules, right here, right now. And if you add work to a system, it adds to the energy of the system. The energy of the system comes in various forms. So conversion of energy is actually one of the key ideas that we need to look at. Okay. There will also be wastage of energy due to non-conserving forces like friction. And we also look at issue of power. Notice that this is not a one unidirectional arrow, not energy becomes power, but it's a two direction. That means you need to consider power as a form of measuring how good your efficiency is. You also want to see what's the instantaneous power, what's the average power. Okay. Right. So this is the overview. Today we will be covering work and a little bit of energy. All right. So as per all physics lectures, at the start, when we introduce a new topic to you, we will give you a definition. Okay? So this is a work done by a constant force. You already know this, that the work done is force multiplied by distance. Okay? The key word here is actually the magnitude of the displacement and component of the force parallel to that displacement. So straight up, what is it? If you look at this example, work done is force and distance, very easy. You look at this example, the force is actually at an angle to the displacement. Am I right? How many of you have seen the second picture before in your secondary school? Huh? None of you. One more time. How many of you have not seen this in your secondary school? Okay. So there are some. So if you see that the force is not parallel to the displacement, you will need to resolve the force. Alright, that means if this is 10 newtons, you do 10 newtons cosine theta multiplied by the displacement. Okay? Right. Does F sine theta give any work done? F sine theta, the force will be this direction, but the displacement will be to the right. The force is up, but the displacement to the right. Will there be any work done? Answer will be no. Because the force will be perpendicular to the displacement, right? So here are some other points about work done. The units in joules. Work done can be positive, negative, right? Positive being is adding to the energy of the system. Negative is removing energy from the system. So the force is actually opposite of the displacement, right? So here are some other examples. Right? In track and field, we do a lot of this. Right? Oh, my sprinters, where are you? There's one. Bruce is not. See, so different kind of sled training, okay? So you big force, take very big steps, put a very heavy weight. Okay? So these are some of the things they do. So we make our sprinters run down the track like this a lot of times. Quite serious. Alright, so imagine now you have a wooden block resting on a frictionless surface. Okay, example 1. Right, you apply a force of 20 Newton to it over 10 meters. Right, I'm rushing a little bit, right? Not as much fun and laughter because not enough time. But you have two angles here. You have theta equals to 0 and theta equals to 30 degrees. So this is a warm-up. I think the first part, all of you should be able to do it. The second part is the one that I want you all to try. Okay? So for angle equals to 0, straight away you should get 20 times 10, 200 joules, but express it in standard form. You should get this. The other one, if you sub in the formula, F cosine theta, right, it will be. Is it always cosine theta? It depends on where your theta is. In this case, the theta is just nice the angle between the horizontal and the F. Right? If it's between the vertical and F, then it's sine theta. So you need to know actually which trigonometric function to use depending on the diagram. So interesting, you apply the same force over the same distance. Well, not exactly the same force, but at a different angle. The magnitude is the same. You realize that the work done is different. So strange, right? Is it strange? Okay. you apply the same force, you feel equally tired. But the work done is different. Why? You'll see that later. You'll see that later. Alright, so this is a warm-up, should be quite easy. Example 2, look at the space. So this exam technique I'm going to teach you. If you look at the exam and the marks they give you is 1 mark, do you write a 10-page essay on it? No. You look at the space I give you for this example. Can you tell me what's the answer? 1, 2, 3? Alright, very good. Answer is 0. In fact, I should say 3, 2, 1. Okay, never mind. 3, 2, 1. Okay. So answer is 0 because it's perpendicular to the displacement. Okay, quite easy. The fun one is the third one. The fun one is the third one. You need to copy word for word because you understand the concept already. We should spend time on those that you don't understand. Okay. This is the fun one. So here you have a block and it slides down 2.5 meters along the slope. Okay, I give you the diagram in your notes. But in an A-level exam, they may not draw it out for you. They will just have the text block. Are you able to draw the figure out? Yes, you should be. Okay, but here, because the lecture is focusing on work energy power, I shall not make it more difficult for you. Right? In fact, you can put all this without describing the forces for you, right? Without telling you which is the direction of the forces. But here, I make it all easy for you. I draw all the forces here. Right? That's something you need to learn to draw. Anyway, here is it. You have 3 forces acting on the block, and the block moves 2.5 meters. Work is always force multiplied by distance, and here there's a distance, here there are 3 forces, so each force must have done some work. That's the first thing that we can say. So my question is, what is the work done by each of the forces? Right, so look at it. Work done by the force of gravity. The first one straight off the bat is the hardest. Why? Because the displacement is this way along the slope, whereas the force is actually straight down. Right? Second one, B, work done by friction. This is actually quite easy because they are all in the same plane, friction and displacement. Last one is work done by the normal force. This one also should be quite easy. I give you 3 minutes to try. Okay, very good. Question part A and B should have gotten. I saw a lot of people do. By the time I reached there already, some people finish already. But they found the trap I set for you. Alright, so I'm a good trap setter. So there you go. The first part is the toughest because you need to resolve. Well, once you get used to it, it should be quite easy. So there are two ways around it. You can either resolve the weight to the slope, right? Or you can resolve the horizontal distance to the vertical displacement done by the object. So it has two ways. I chose to do this because I know this is more rare. Right? So most of you will actually resolve the force to the slope, which is just W cosine 60 degrees. It's not a problem. Right? But either way, you should get back the same thing. If you use work, so here there are two W's when you copy your handwriting. One is work, capital W, one is W with big. Too small so they can show the difference. So the work done is just force times the displacement times the angle between them. And since the angle is 60 and it's 2.5, you submit everything, you get this answer. Okay? Even if you have resolved for the force, you should still get cosine 60 as the angle between them. Right? Most of you should get this answer. Also, please take note, G is no longer 10. G is no longer 10. The second part, give you a hint. If your answer don't have a negative sign, you're wrong. How many of you got trapped like that? Part B, I was looking around, I saw a few. Okay, so part A done. Moving on to part B. Part B, you realize that the displacement is forward, downwards, whereas the friction is backwards, right? So if that's the case, the work done by friction must be negative. You must be very careful of this. Right? You must be very careful of this. So your answer, if it doesn't have a negative sign, you got it, right? You got it wrong. And number PC is just basically 0 because it's perpendicular to the displacement. Okay. Alright, can I move on? Now, when is work done? I've shown you work done by a constant force. Maybe just not parallel to it. Now I'm going to show you work done by a variable force. And in fact, you've seen this before. Right? When I push a block along the floor, well, I'm not a robot, right? My force can never be constant. Right? You will agree. Right? Even the floor will not have the same friction along it. So the force will go up and down, up and down. So what's the work done? Well, the work done is always the area in the force distance graph. Okay, I say again, very important. If you see a force distance graph and they ask you what's the work done, all you have to do is to find the area between the 2 points being considered. Okay? So here, if you think that the delta x becomes smaller and smaller, you can just simply say mathematically that it is the area. Right? It is the area. If you think about the area from here to here, we can just split up many columns and say it's the area behind it. Right? This is a calculus. You'll be learning in math. Right? So don't say it's simple. It's just the area on the graph. Right? Area on the graph. If all things fail, use count the box technique. Right? Usually you have graph paper. If all things fail, but you should have mathematics skills. Right? Okay, going on. Now, I want to show you a certain example, and I think you were shown this by some other lecturer before. Right? Oh, it's me. Right, this is Hooke's law. Hooke's law, I gave you a fx graph, right? Fe graph is the same thing, it's the same thing, right? So, if I give you an Fe graph, the force displacement graph, the area under the force displacement graph is the work done, right? It's the work done. And the work you do goes into the energy of the spring. So we say that the elastic potential energy of the spring is half kx, is half fx, or half fe, the same thing. E is equal to x in this case. Right? Half fx. Right. So that's for spring. For what about for gas? This one is something new. I want you all to wake up to a start here. Very important. We have been saying that work done is force and distance, force and distance, force and distance. Okay, enough already. Millions are bleeding, right? But here you have a piston, a frictionless piston with air inside. Okay, if the gas expands, moving from the inside out, okay, and the gas expands from a smaller volume to a larger volume, being this where it is now, the dotted line is where it will be later. Okay, what is the work done by it? What is the work done by the gas? Well, do you have force and distance? Well, yeah, you have force and distance, but for a gas, right, usually what is easier for you to see, because it's a string, is actually the volume change and the pressure of the gas. Right, so are you able to work it out? Or I'm going to show you how. Okay, we'll go. If you look at the work done, right, work done is force times distance. Because force is just pressure times area, right? Agree? Just pressure times area. We assume constant pressure outside. Okay, so force is pressure times area. The distance will be delta x. Fine, cosine theta is just there, it's there. That goes to 1, so just don't care about it. If I regroup the brackets, I can put pressure times A delta x, area delta x. And the area is the cross-sectional area of the piston times delta x. And delta is that B. Cross-sectional area times the delta x is actually the change in the volume of the gas. You should see again. Right? So that's how I get to this equation, which is the change of the work done is the pressure times the change in volume. Okay, the pressure times the change in volume. Okay, please make sure that your things are in the correct units. So this is for constant pressure. There was an A-level question that asked the MCQ question, and what the answer was that in this case we use this equation. What must be the assumption? The assumption is that the external pressure must be constant. Okay, the external pressure must be constant. So this is acting under assumption that external pressure is constant. Right. What if I give you a pressure PV graph where it is not constant? Well, it doesn't matter, right? You look before. If we know that work is P times V, in the PV graph is the area at the PV graph. For a curve, it's actually still the same idea, right? By calculus, it's the same thing. So even if you are given a curvy graph, the work done by the gas, right, as it extends from V1 to V2 will be the area under the PV graph. Okay? And right, so let's have a question. This question is a bit tricky. See, let me guide you through it. Find the work done by the gas. Okay? I always say see if you remember. Here I say the work done by the gas as it expands from V1 to V2. So V2 is bigger than V1. But you look at the question here. The work done by the gas, when the volume becomes smaller. Oh, so the work done by the gas cannot be positive. Okay, if the gas expands, the work done by the gas is a positive number. But here, the gas contracts. So the work done by the gas must not be a positive number. It must be a negative. Alright, so try it out. Okay, moving on. Answer will be this. Okay, it's a negative sign, right? In Thermophysics 2, which is your last topic before the exam, right? You will learn a lot more about it. But here is just a heads up, my advertisement trailer, movie trailer. So exciting. So I've done this with you, I've done the work with you. Now I can move on to energy and the various forms of energy, okay? Various forms of energy. There are many forms of energy and we all know it. We all know it. There's chemical energy found in your food. Every day many of you will consume chemical energy in the form of rice, pasta, fried fish, pan fried fish. Okay? Nuclear energy. Recently in the news, I do some EP review. What is Singapore trying to do with regards to nuclear energy? Sorry? Don't know. We are trying to, the National Research Foundation. So this is good news for physics students. The National Research Foundation wants to group 100 people to be very good at nuclear energy. If you think about it, if you want to first group 100 people who will become very good at it, what does it mean? But they need to have some job, right? That means there might be more development in this area later. But it's quite scary for Singapore. If you have a nuclear power plant, you think about it, it's quite scary. Radiant energy, right? Those of you who have sunbathed in the sun before and forgot to put suntan lotion, or just you know how this feels. The energy actually fries your skin. Electrical energy. How many of you have not seen a lightning before? How many of you have not heard the lightning before? You don't hear the lightning. Very good. You hear thunder. Good again. Solar energy, mechanical energy. So there will be two forms of energy that I brought up that we can actually quantify very clearly in our physics, right? Internal energy will be covered mostly in thermal physics. So don't worry, we'll be covering mostly mechanical energy in this lecture. There's also mass energy, right? So let's talk about mass energy first. It's the most famous equation. E equals to. Right, okay, so yeah, you already know about it. Fine. How many of you have seen Hawk, the movie? Hawk, the movie. Right, Hawk angry, Hawk smash. Yeah? When the Hawk so this is where as a being teacher, right, I get very irritated, right? When I see Hawk grow so big, right? The Hawk, is it a Hawk? I don't know how you pronounce it. Whatever. When he grows so big, right, he gains a lot of mass, right? That means in an instantaneous manner, he can gain energy from the surrounding. Right? I did some calculations, right? As I was watching the movie, I did some calculations in my mind that he's gaining this amount. Because he looks a bit like me, then he becomes suddenly like a monster, 4 or 5 times my size, right? So his mass probably went up to 500 kg, right? So if I use that by c squared, what's the energy? Then okay, the air around him must cool down to negative 3 million degrees. That cannot be. Because the atmosphere is very looking like, so this is all wrong. Like, I hate this movie. Okay, next is chemical energy, right? You have the oil, very big industry in Singapore, Jurong Island, almost every day using this. Chemical energy, dry cells, food, glorious food, yes. Nuclear energy, yes, I mentioned this just now, right? I think something's really going on. I don't know about it, but I think something's going on. Also, there's the other kinds. The most recent one, which is the disaster, right? Very sad. Is where? Fukushima. as an engineer and a EPC, right, I know that we can make nuclear energy safe. I know we can. The question is at what cost? Right? Is the human skills able to keep up? Are we able to work like a robot consistently to try to make it safe? Right? In the off chance, 1 in a 10 million, 10 billion chance, anything happens very scary. Radiant energy, you see before. Solar panels. So solar panels directly convert the sun rays into energy, right? But there's a different kind of solar panel. In the in the Nevada desert, right, or in the Spanish desert, they set up mirrors instead. This is solar panel. We convert electrical sun energy to electrical energy straight away. Solar energy. The other one is mirrors. They have a whole range of mirrors, and they zoom it right to a vertical tower to heat water in the boiling tank. In a tank, they just focus, all the mirrors, right, will focus the sun rays onto one particular point. Any of you have used a magnifying glass to fry beef before? Right? They focus the sun in to burn something. That's exactly the same concept. Same concept. We say 10, then I say 5. But that has a very big problem, right? Imagine you're a bird. Imagine you're a bird, you're flying. What a nice day. And you're flying through this solar farm. Then there's a death ray of beam of sunlight, right? It just forecast. One moment you're happy, the next moment you're fried, literally. Because the amount of heat passing through is incredible. It's literally a death ray. Right? So there are a lot of green rights movement people who like say, stop this farm. Okay? Because they don't like the mirror version. But the mirror version is better. Why? Because it saves a lot of energy. One electrical panel like this costs a lot. So there's a lot of pros and cons either way. Okay, next. Internal energy is the energy possessed by atoms and molecules in the matter of kinetic and potential energies. The intermolecular kinetic energy and intermolecular potential energies. This one, we will talk a lot about it in Thermal 1 and Thermal 2, so no worries. What I really want to focus on is the mechanical energy. Okay, so get this to the head. Mechanical energy is the sum of kinetic energy plus potential energy. I say again, mechanical energy is the sum of kinetic energy plus potential energy. Right. Very good. I'm really going quite fast. Right. So there you go. Kinetic energy, and this is the first thing that you must hear. In secondary school, how many of you have learned that kinetic energy equals to half m? Very good. How many of you derived it? Good. Alright, good job. Bruce, you have a lot of supporters. Hey! Alright. So in this lecture, right, if you flip to the first page, you realize that you are asked to, you are required to, you must derive kinetic energy. That means secondary school you use it, right? In JC you learn to derive it. Okay? It's just like now you're using cell phones, handphones, smartphones. Maybe next time you'll be designing it. Right? The same idea, you get one step of it. So here you go. If I apply force on a block over a certain distance, we know that I'm doing work to it. The question is, where does the work go to? Right? So if the floor has no friction, right, my force will allow me to accelerate the block with a constant acceleration A. Do you agree? Yes. Very good. Right? So in that case, so we hold that thought first, then we move on to kinematics. Okay? In kinematics, we've already learned and established that E squared equals to U squared plus 2AS. In this case, the S is the delta, is the movement by the block. So I can rearrange this delta S to be in this form. Okay? So now I combine it together, and this is where the concept is. Okay, this is where the concept is. In the law, this is where the concept is. So please listen carefully. The work done by me is the force times the distance traveled by the object. Okay? And I know, using Newton's second law, that the force I've applied must be equal to ma delta x. Right? And I also know that I can sub in delta x for something else that I learned in kinematics. Alright, so there you go. If you sub in what you have learned in kinematics, ma delta x becomes this chunk. The net work done will be equal to half mv squared minus half mu squared. Quite amazing, huh? That means from what you have learned in secondary school, some of you already can basically derive kinetic energy. Some of you basically can already do it in secondary school. But now I show you. Okay? And we can write that the work you do will cause a change in the kinetic energy. This is a final kinetic energy. V represents final velocity, U represents initial velocity. So the work that you do will be the change in kinetic energy. And this is what we also call the work energy theorem, that the work you apply to the object results in the change in kinetic energy of the object. Okay? So here, if you assume that all the work is constant to K, there's no friction force, and that the initial kinetic energy is equal to 0, can we straight up say that the kinetic energy is just half mv squared? Yes. Right? Because we know that our work done must become K. Our work done must become K. So work done equals to that chunk of equation which becomes this. And we know that work done becomes K. Work done is K. So K must be equal to this. Okay? Okay, moving on. The first part is just a warm-up question, right? You have this mass, you have this velocity, what's the energy? So I see example 5. The hard part example 5 is the part that comes behind. It's asking you, what is the resistive force offered by the target? So if I do this, someone shoots a bullet at me, right? And I stick out my hand to block it. Alright, so from the front of my palm to my elbow is about 40 cm. Okay? So the bullet comes into my hand and travels for 40 cm. I want to stop it now. If it goes for 1 meter, my head will be gone. So I got 40 cm to play with. Right, so what if I stop it in 40 cm? My hand must have applied a force on the bullet. Agree? My hand must apply a force on the bullet to stop it. My hand has applied a force as the bullet travels in, the work done must be negative. To remove energy from the bullet. You see the concept here? The kinetic energy of the bullet is reduced to 0 as I apply a force backward. It's the opposite of me taking the bullet and pushing it forward with the distance forward. That adds to the kinetic energy of the bullet. This is the opposite. Okay? And the question is what is the resistive force offered by my hand on average? Okay. And I've given you the answer. So in my notes, I made a mistake. The line that I drew should go above the line K of the bullet because that is part of the answer. Right? The K of the bullet hitting the target, that's part of the answer. The third line is the answer. So my line must go above it. Okay? So my mistake. So Ke of the bullet is half mv squared. Sub in, you get this value. This is no kick, seriously no kick. Okay? The Ke of the bullet is expanded to do work to overcome the force of it. That is what you need to relate. The conversion between energy to work done. So the work done by my bullet, work done by me to stop the bullet will cause the bullet to lose its kinetic energy. Okay, so my force and the distance of 40 cm is 180 degrees from each other. K final, K initial. So I see that my initial Ke is a lot, it's positive,
K final is 0. My force is negative because cosine 180 is negative. The distance is 40 here. I rearrange, I solve, I get that my force is 9.4 kilonewton. That means my hand must be able to apply a force of 9400 Newton. My hand must be able to apply a force such enough to carry 940 kg. Not very likely. Okay. Right. So the important part of this example is the concept here. Can you put a little star, highlight, whatever? Is this concept here? That the energy of the system can be reduced by applying work in opposite direction and externally. The work you do on it can either increase the K or reduce it. In this case, I'm reducing it. Okay? Okay, ready? Done. Right, so this bullet right is traveling in a horizontal mode. What about this? Have you seen the movie Iron Man? How many of you have not seen Iron Man 1? You poor thing, if you have not seen it. Please go and see it. It's very, very good. The rest are just not so good. I like Iron Man 1 just because it's the number one, the first one. Right, and in this show, Tony Stark, he built his first suit, right? His first Iron Man suit in the cave, right? And he was flying out. But it's a prototype, right? So it's a bit, the materials are very bad. He has well everything, right? So he's flying the sky, and here, the machine malfunction, right? What happened? He fell, right? Fell, and this was the exact picture. Right? I wanted to get a video, but I don't know how to do it. Maybe you all can send me. Check that clip, just that clip. The part where he fell out of the sky and landed the sand. Now, the bullet I was talking about, right? The bullet I was talking about was traveling horizontally and stopped by my hand. Tony Stark is like a bullet falling down vertically and going to the sand. Am I right? Now, at this moment of time in the movie where I was watching it halfway, and I saw this scene, and I said, oh, throw over. I said, I'm over to that. And Tony Stark kind of like, because as a physics teacher, right, the moment we land, it's dead already. I show you why. Imagine you are so high up. When you fall to here, how much kinetic energy do you have? A lot, right? Right, this suit plus himself, wow, I don't know how many mass, maybe say 300 kg. Height, let's just put 1 kilometer, 1 kilometer, mgh, when you reach here, what that be a lot. How deep did he sink into the sand? Until here, say around 1.2 meters. I give you 1.2 meters. What is the force did he feel? What force did he feel? Average force did he feel to resist, to slow down his energy to let it come to 0? It's in the order of 10,000. 10,000, 20,000 Newton. That means his body must be able to carry, a normal human body must be able to carry 1,000 kg of mass. Not possible, right? So at the point of time when he fell in, I did some mental calculation. Yeah, the force is feeling now is around 1,000. Okay, about 10,000 Newton. 10,000 Newton is my force. Yeah, going like this. I said, about to A, cut A, I meant A. Yeah, I was so sad, right? All laws of physics. All the Hollywood movies, after my lectures, you will see all Hollywood movies differently. I'm sorry to spoil all your future Hollywood action movies. But all the physics there, everything is a good easy one. Alright, anyway. Sorry to spoil all your future movies. This is another example. Right here, you have a car, 2,000 kg moving down a level highway. It has two forces, right? There's actually 2 forces. Actually, there are 4. But the N and W, we don't really care about it because it's the vertical mode. In the horizontal mode, there's a 1,000 Newton force forward, that means F is 1,000 Newton, and there's a friction of 950 backwards. Okay? Using work kinetic energy theorem, well, even if you don't know it, right, I can ask you, find, even if you don't do it this time, find the speed of the car after it has moved 20 meters, assume it starts from rest. That means these 2 forces, 1,000 and 950 is applied for 20 meters. What is the kinetic energy of the car? Okay, what is the kinetic energy of the car? Okay, try it out. Okay, very good. I saw some of you with the answers already. So this is all the talking lah, all the thinking. Right, in a real exam, right, you think but you don't write. Okay, this is all the thinking. Okay, first the force is forward, okay, so that's 0. This force is backwards 180 degrees, so it must be negative. Right? Or you can just consider the net force on it. The net force on the object will cause it to get some gain in energy. So the net work done on the car is just the forward force minus the backward force, the 20 degrees. 20 meters. Right? This is the net work done by me. And I can equate this to be the gain kinetic energy of the car. I can equate this to be the kinetic energy gained by the car. You'll see a little, see got people talking, so I'll wait for one more. So I'm giving you very detailed instructions here on how, step by step. Always write down the equation, start in the values, give the answer. Right. Moving on, the work energy theorem then tells me that the work I do must be equal to change in kinetic energy. And since the initial energy is 0, it's just half mf df squared. I rearrange for v as a subject. I sub in everything, I get 1.0 because if you any one of you wrote 1 SM, wrote 1, wrong. Never leave your answer to 1 SM. Even if it's exact, you write 1.0 or at least 1.00. Right? Never leave your answer to 1 SM. Okay? Right. So this is kinetic energy. Right, most of you have done some of this before, but we're using kinetic energy straight away to work, and we're talking about changes in conversion energy, and we are asking you to derive kinetic energy. Right? Next one is potential energy. You also must learn how to derive it. So I'm going to use the same trick as I used for kinetic energy. Let's consider a book near the surface of the Earth. If I want to increase, when I move this book from H1 to H2, I said that I have increased the potential energy of the system. But where does this potential energy come from? Well, it must have come from the work I've done, right? It must have come from the work that I've done. So, these are the conditions. I must assume that there's no air resistance. I must assume that the book has constant speed at the start and at the end. So there's no gain in kinetic energy. When this two is true, I can then derive my potential energy gain as such. First, the work I do will be the force I apply times cosine theta delta x. Right? Just always use this equation. But this force is just equals to mg. This force is just equals to mg. Why? The force I apply to raise this book up is equals to mg because I do not want it to gain kinetic energy. I want the forces to be equal for it to move up but not gain kinetic energy. Okay? So the force I apply, magnitude is equal to mg. The height I move through is delta h, h2 minus h1. And you get work done by you is mgh minus mgh2 minus mgh1. So I've derived for you the equation that you're using since secondary school, mgh. How do you derive it? Like this. It's actually very simple. The only and the same concept as kinetic energy is that the work you do must will and is the potential energy, and you can derive it out through the work, through the force and distance equations. Okay, with necessary assumptions of course. So here, if I assume that at height h1 the potential energy is 0, or I just reduce h1 to become 0, the work you do becomes mgh2. Easy, not a problem. Right, so work done is mgh. Done. So here you must always choose to set a reference point. And that is a skill. You must choose a reference point that makes sense. If I have an object on the ground, I will choose the ground as potential energy 0. If I have an object on the table, I will choose the table as potential energy 0. Right, so it's always a reference point. And this is also true. You must take note. It's only true when it is near the surface of the Earth. When you go into outer space, it's something else. Right? And you will learn that in gravitation. There are also different forms of potential energy. Right? I leave this bottom up because it has mass, is gravitational potential energy. When there's two positive charges, I bring them very close together, they want to fly away. I also increase the potential energy by electrical potential energy. I stretch a rubber band, right? There's elastic potential energy due to the intermolecular interaction. So these are the other forms of potential energies available. Right, don't think we have enough time, so we should leave the example to next lecture. We leave the example to next lecture. So please go home, review your notes, and try example 7. Please try example 7.